All right, I'd welcome everyone back to our first technical session. We'll have a couple of presenters here. I would hold all questions. You can type in your questions and answers to the Q&A section, but we will hold off on answering all of those to the end. So with that, I would introduce Dr. Royce Floyd as an associate professor in the School of Civil Engineering and Environmental Science at the University of Oklahoma, and is a registered professional engineer in Oklahoma. Currently, his research is focused on extending the life of transportation infrastructure using innovative concrete materials, such as ultra-high performance concrete. He has been PI or co-PI in more than 15 projects sponsored by ODOT, SPTC, and the ABC-UTC, focused on bridge behavior, evaluation, and repair. He teaches courses on engineering mechanics, reinforced concrete, pre-stressed concrete, and structural wood design at OU. He's a member of the Association American Society of Civil Engineers, Precast Pre-stressed Concrete Institute, and the Concrete Institute. With that, Dr. Floyd.
Good morning, and thank you for this opportunity. Thank you, Rick, for that introduction. I'm going to try to get my slides up here where you guys can see them. Let's see. All right, there we go. So this morning I'm going to talk a little bit about non-proprietary UHPC or ultra-high performance concrete for transportation structures. You all have heard a little bit about UHPC this morning. You'll hear a little bit more after this presentation, but I'm going to talk about some of the work that we've done at OU and with some of our research partners over the last few years. So the question is, what is UHPC or ultra-high performance concrete? And it's a cementitious composite with steel fibers included in it. FHWA defines UHPC as having a compressive strength greater than 21.7 KSI and having a post-cracking flexural strength greater than 720 PSI. But we can kind of extend that definition to a more general definition as that cementitious composite with a compressive strength between 18 and 30 KSI. And still having that high post-cracking strength of 700 to 900 PSI. It has a very high flowability, a very low to negligible permeability, and minimal freeze-thaw susceptibility, which leads to a very high durability and hopefully very extensive long-term performance. And those steel fibers included in the matrix not only help with tension strength, but also provide some impact resistance, which can be very helpful in some transportation applications. So the motivation for the work that we've been doing at OU originally came out of a lot of problems that we were seeing with bridge joints throughout Oklahoma. We have, a lot of deteriorated bridge joints in Oklahoma, and you can see an example here on the left of a bridge joint where we're losing some of the steel armoring. The joint has started to close up. We can see some spalling of the concrete around the joint. And then on the right side, we can see that the bridge deck slabs have kind of offset, creating a bump there in the road. Our joint sealant material is coming apart, which is going to allow water to get down onto our bridge structure. So the thought was to use UHPC as an expansion joint header. We can see here on the left a header made of an elastomeric nosing material. In the middle, we have a section that we replaced with a proprietary UHPC material that we've been monitoring for about 3 years now, and it's performing very well as a joint header. It is a material that can stand the impact by itself. You could come back in and grind it if the slabs start to offset, so we can keep a smooth transition. We also see a lot of in-region deterioration in precast girders in Oklahoma. That comes again from those leaking joints getting down onto our beam ends, causing corrosion of our pre-stressing strands, exposed steel, spalling of the concrete, which can affect our shear capacity, bearing capacity, and pre-stress transfer at the end of our beams. We have a lot of bridges that were originally made continuous for live load using linkage blocks between the girder ends that cracked over time due to creep and shrinkage effects within the precast girders. Those can lead to an additional way for water to get into our beam ends to cause some corrosion and deterioration. And we also lose some of that continuity once those start to crack. So the thought is that UHPC can be used to repair these applications or repair these deteriorated locations. And this has been done for steel girder ends. It's starting to be looked at for concrete girder ends. There's some research that just came out recently using it as a patch repair for beam end regions. You heard a little bit about work FHWA is doing in that area. And this is another application that we're looking at here at OU. There are lots of other applications for UHPC that you'll hear about in the next presentation. Bridge deck overlays, girders made of UHPC, joints between bulb T girders, joints between full depth deck panels, and then seismic force resisting elements are all great examples of UHPC. So there's great UHPC out there, proprietary materials that have a lot of technical support from the manufacturers. So the question then is, why non-proprietary UHPC? And the reason that we're thinking non-proprietary UHPC and why this is a topic of interest across the country is, for one thing, the superior mechanical properties of the very high-end UHPC may not be needed for some of the applications, such as field joints and bridge decks. So we may not need, a compressive strength of 25 KSI. We may just need a very good bond strength. We may not need a very high bond strength even. We may just need a very high durability. So the goal is to be able to tailor the properties of our UHPC to the particular need that we have, which can potentially lower the material cost. And then, proprietary UHPC can lead to sole sourcing and bidding issues. So if we can develop materials with locally available constituents, we can increase accessibility to UHPC, especially for, say, small repair jobs done by a maintenance crew. So our objective and goal was to work with ODOT as well as our ABC UTC partner universities to examine non-proprietary UHPC class materials for multiple applications. Our specific objectives started out with developing a UHPC mix using materials locally available in Oklahoma. This was work that we did with ODOT. And then we worked with our ABC UTC partners to examine a more general non-proprietary UHPC mix that could be used across the country. We then looked at evaluating that mix performance and repeatability using FHWA recommended material tests for UHPC, as well as some structural testing in various applications. And then as part of that, we looked at the effect of different steel fiber contents on the material properties and structural behavior of our non-proprietary material, because steel fibers are by far the costliest element in a UHPC mix design. Just kind of giving you an overall picture of what this project has entailed. We've been working with the ABC UTC for the last couple of years. We started at OU in mix development, again sponsored by ODOT. We've done a couple other projects looking at specific applications for UHPC, but we've done a lot of material testing, bond testing, and some structural testing at OU. But we're also working with Iowa State University on durability, University of Washington on shear behavior, University of Nevada, Reno on full-scale deck panel joints, and then Florida International University looking at material testing for UHPC made with materials locally available in Florida. We also shipped our locally available Oklahoma materials to our partners across the country. They shipped materials to us so that we could examine the effect of different local materials on the performance of our UHPC mix design. So kind of looking at the different things that we've done, starting with the mix development, we looked at a significant number of potential constituents available in Oklahoma, including type 1 and type 3 cement, fly ash, slag cement, and silica fume as our supplementary cementitious materials. We used a very fine masonry sand because we wanted a really small particle size to fill in all the gaps within our matrix. We considered a couple of different high range water reducers as well as different commercially available steel fibers. We started with some initial mix designs that were based on previous research from various groups across the country. And we took all of our materials, applied them to those mix designs, evaluated the performance, and then looked specifically at what we had to work with, our different possible constituents, and looked at optimizing the particle packing of the different gradations of those materials. We looked at about 3,400 different possibilities virtually to find the best particle packing for our materials. And then we also looked at the reactivity of our different cementitious materials to determine what would help us get the highest compressive strength. That resulted in a baseline mix design that consisted of type 1 cement with 10% silica fume and 30% slag cement by total weight of cement. So we had a high percentage of slag within our mix to replace some of that very expensive cement. We had a water cement ratio of about 0.2. We had masonry sand at a 1-to-1 ratio with our cementitious materials. And then our baseline mix had 2% steel fibers by volume and high range water reducer in the amount of about 18 ounces per 100 pounds of cement. And here on the right, you can see kind of the mixing process for UHPC, where we go from all these powder materials. There's not very much water, so it takes a little while to mix, starts to ball up, and then eventually gives us this nice flowable cake batter-like material. So once we had the mix design developed, we extensively examined the material properties, including flowability as a fresh property, compressive strength, modulus of elasticity, splitting tensile strength, flexural strength, direct tension, shrinkage, creep, set time, and then for durability, we looked at freeze thaw resistance, rapid chloride ion permeability, and we did some corrosion testing. So kind of just going through a few of the different properties of this mix design. We started by looking at the flow. We looked at it in terms of the percentage of steel fibers between 0% up to 6% steel fibers. We also looked at the difference between materials from OU, which is shown in gray on this graph, and materials from Florida, which is shown in yellow. We saw a decrease in flow once we got past about 2% steel fibers, even if we added additional high range water reducer. So we went from the picture on the top left, where we have a flow extending to the edges of our flow table, to where we go to 4% fibers on the right, which our flow is reduced, to where with 6% steel fibers, we basically have a fiber ball in the middle of our flow table. In looking at compressive strength, again, OU materials are shown in blue, materials from Florida are shown in orange. We had a compressive strength in the range of about 16 to 18,000 PSI. We saw a little bit of an increase as we increased steel fibers in general. We did see a decrease with the 1% fiber mix consistently, but once we went on to 2%, 4%, or 6%, we saw a modest increase in compressive strength. We saw an increase in flexural strength as we increased the steel fibers, which is to be expected. And in both cases, we saw fairly similar performance between materials available in Oklahoma and those available in Florida. We did consistently see an increase in tension strength, or a higher tension strength at 4% steel fibers than at 6% fibers. Even though it's only shown for the OU materials here, we saw it in our direct tension tests as well. For bond strength, we looked at number 5 bars, number 8 bars, and number 3 bars using both a comparative pullout test as well as a beam splice test. Shown here, we have our different fiber contents, and we can see that for number 5 bars, we have a significant increase in bond strength going from 0% to 1% steel fibers. We don't see a lot of change from 1% to 2% steel fibers. And then once we get past 2%, we kind of flat line on our bond strength. It's very similar for number 8 bars, but we do see an increase between 1% and 2% steel fibers. But beyond that, again, we kind of have a flat line on our bond strength. We compared bond strength with a proprietary UHPC as well. So OU materials are shown in dark gray, a proprietary UHPC in light gray. And if we look at it just in terms of the pullout load for our pullout test, it looks like the proprietary UHPC has a much higher strength. But if we normalize that based on the compressive strength, we get very similar performance to the proprietary materials in terms of bond strength. For durability, we looked at freeze thaw testing of the UHPC material itself with different steel fiber contents. And we can see on the bottom right that we basically had no deterioration out to 350 cycles of freezing and thawing with any fiber content that we examined. We compared it to a proprietary UHPC and found, again, for 2% steel fibers, so our base case, very similar performance. For rapid chloride ion permeability testing, we found negligible and very low for the proprietary and non-proprietary UHPCs, respectively. And then we also wanted to look at what would happen if we had a composite specimen that was conventional concrete connected to UHPC, which is what we're often going to have in the field. How does that interface stand up to freezing and thawing over time? We also looked at some corrosion testing, which I won't discuss here today. But looking at those composite specimens, we found that in every case, we had deterioration in the base concrete before we had deterioration of the interface. And even for the 0% fiber specimens that are shown on the top right, that cracked transverse to the specimen, the interface between the two concretes was still in very good shape. We also looked at some full-scale slab joint testing. We did both static and cyclic loading with elastic level loads to simulate traffic. These were near full scale. And our load deflection behavior showed that we had a slightly less stiff specimen using our non-proprietary mix than with the proprietary UHPC, but we had very similar ultimate capacities, and we did have relatively similar stiffness. The OU material is a little less stiff than the non-proprietary UHPC in general, and the bond to the conventional concrete is not quite as strong. So in conclusions, the non-proprietary UHPC can achieve the superior properties desired for many applications. It has an estimated cost between $400 and $700 per cubic yard, depending on the fiber content, compared to several $1,000s for the proprietary materials. And in our structural tests, we found that we yielded our reinforcing steel with just a 5-inch lap splice and got a strength of our joint that exceeded what we calculated for a monolithic slab. So what we're still working on, we're doing some in-region repair testing currently. We're doing some continuity block repair testing currently. We have some link slab testing upcoming, as well as some work on life cycle analysis for link slabs. We're always looking for places to implement this material. If anybody has something they want to talk to me about, I'd be happy to sit down and discuss that. And then we have a guide for non-proprietary UHPC coming out with ABC UTC soon, as well as a short course and a workshop that will hopefully be ready by the end of this year. So with that, thank you for your attention. Feel free to shoot me an email, ask any questions that you'd like to know more about what we're doing here at OU.
Thank you very much, Dr. Floyd, for that presentation. We're going to go ahead and continue our UHPC conversation, but shift to bridge engineering solution. Dr. Atorod Azizinamini is the Vasant Surdi Professor of Civil Engineering, Director of Accelerated Bridge Construction, University Transportation Center, also the Director of Moss School of Construction, Infrastructure, and Sustainability, and the Director of Preeminent Institute for Resilient and Sustainable Coastal Infrastructure at the Florida International University. He's led several major multidisciplinary bridge engineering related initiatives. He is a founder of 2 major transportation field organizations, the National Bridge Research Organization and the University of Nebraska-Lincoln, and the Center for Accelerated Bridge Construction at Florida International University. He has developed several bridge engineering products and systems that are being used nationally and internationally. So Dr. Azizinamini, thank you.
All right, thank you. Can everybody hears me? Well,
yes, sir.
Fantastic. All right. Always a pleasure to be with my good friends in Oklahoma, since I'm also OU alum. So that gives me a double pleasure to be with you today. And thanks for my good friend, Dr. Musharraf Zaman, to give this opportunity to share results of some of the work that we are doing. As Royce mentioned, ABC UTC is a university transportation center, Tier 1, and you see our partner universities, and University of Oklahoma is a very important and a good partner for us. And in fact, Royce Floyd is a principal investigator that is conducting the basic development of the non-proprietary UHPC. So what I would like to do is really just give you the list of some of the products that we are developing that are using a UHPC. I personally strongly believe that the future of the bridge engineering is really tied very closely to UHPC. It's not that we are going to be building the entire bridge using the UHPC. I think strategically it has a very good applications, especially in the retrofit, connection, things like that. So I'm going to go through some of them. So I apologize if I don't give you all the detail because of the timing, but I will be more than happy to provide any detail that if any of you are interested in, as you see. So it's very easy to get in contact with me or even Royce. Okay. So just to give you some list, one of them in the ABC, the common sense in the bridge engineering says that the less connection joints you have, the better off you are. And here in ABC, the modular approach is one of the most widely used, and we have joints all over the bridge. So the UHPC, because of the durability aspect of it, that really nothing penetrates to it, is the best option to use in the joints. And that's where you improve the durability of the ABC type projects. One of the area is the connection between the cap beam that you see down here and the precast columns. There are many different options. One of the best options that we have developed is really connect everything in the outside, basically outside the element. So, and here you can see several different options. There are, for example, a coupler, things like that you can use. If you want to basically penetrate inside the cap beam, the steel cage is so congested that you really cannot do much. So our solution really is that we say, okay, bring the reinforcement outside your cap beam, and you have the reinforcement outside the precast columns. And then, as you see over here, basically connect them using a layer of UHPC. And that's the best thing you can do. It has many different advantages. So we have done quite a bit of a testing. Basically, all these photos shows you that this type of connection works, and the damage is always above the area where the UHPC is used to connect the elements together. And we have also developed a very simple design formula. We say, really, all you got to do is the overlap basically is the length of the splice is 8 times the diameter of the bar, and the cover you need is 2 times the diameter of the bar. Now, the beauty of this connection is that you don't need to worry about the tolerances because you're really splicing. And if something is out of tolerance a little bit, you're not going to have a problem in the field. So it's again, UHPC provides you a very good option in this case. Another area that I strongly feel that it's going to be really, that's where we are going to be using the UHPC in future. And that is the retrofit. I mean, the fact is that we don't have that much money to replace all the deficient bridges. So what is the option? Well, let's just use some material that we can bring the deficient bridge elements even to the condition that are performing and providing you a capacity better than the original structure. And that's where the UHPC comes in. So we've done quite a bit of work. So we have actually a guide for how to utilize these things. Now, let me also say that use of the UHPC for retrofit is not new. 2 years ago, I went to Europe with a good friend of mine, with Professor Hale in Switzerland, and we looked at the number of the projects where they have used in Europe for UHPC for retrofit the deficient bridge elements. So it has been used over the last, probably I would say 20 years, and they are providing great performances. And the good thing is that when you use the UHPC to retrofit, the finished product is even better than the original structures because this material has so much strength and such a great durability character. So what I'm saying really for retrofit is something that the Europeans have used quite a bit. And we've done lots of testing. You got to be careful when you retrofit these things. The material is so strong that the mode of the failure can shift from one region to another, even can damage your foundation. So you got to be careful. If you design it correctly, this picture on the left to the third picture over here shows that in this case, we have to beef up our foundation a little bit. You do that, it's a wonderful material for retrofit. This is an example of retrofitting columns. Another area, retrofitting of the flexural beams. So we have developed several different options. And if you don't want to remove basically lots of material, you may need a mechanical device in order to get the UHPC to act compositely with the normal strength concrete. But if you can remove the concrete to the level where the transfers, reinforcement, and so on is available, then you don't need the mechanical devices. That's all this picture is saying. So the option really for flexural beam is just wrap it with the layer of a UHPC and flush it against the surface. Here's again some of the photos, and we've been getting great results. Another approach, in fact, this material is so flowable that you can wrap the entire element with the UHPC. For example, here, we actually build a glass formwork and then place the deficient, let's say, beam representing a deficient, maybe a girder in a bridge. And we were interested to see if this concrete flows, okay? And I'm not sure if you can see this video. So in fact, this took a long time because we had to mix the concrete and then fill it with the dump it using a bucket. So even using this long process, we didn't have any honeycomb or anything like that. This UHPC flew around the formworks, filled all the gaps, attached compositely with the existing deficient structures. And I can show you, this is the end products very nicely. Now, for those of you who are worried about the long-term performance, I think there was one question that asked. We have a faculty, Dr. King's Law, that is doing lots of corrosion study with this material. I can tell you that this material, the long-term performance of this material is excellent. The reason for that is that because this material chokes the system, doesn't let the oxygen and the water to exist at the same time. The so-called corrosion people are really sensitive about this halo effect. There is no halo effect when you repair an element using this material. So the long-term performance, we've done work in this area, other people have done work in this area, is excellent. And in fact, what you're seeing over here, this green shows the same T-beam as it was, and then this one by wrapping only an inch and a half of UHPC around it. You can see how much strength this gains. So not only you increasing the durability of the element, but also the strength. So it's in that sense, I'm saying that the future of the bridge engineering very closely tied to this UHPC. Another concept we have come up with is replacing the formwork with the UHPC. So another way, rather than building my formworks using what you see over here, use it with a UHPC shell. Bring it to the field, connect them together, and then fill it, place your reinforcement and fill it with the lightweight concrete. So this is schematically basically showing this. You precast basically a shell, represent a column. You bring it over here, you connect them using the UHPC connections. Here's a cap beam. You put it on top of the precast shell for the column. You put the reinforcement, you place the concrete, and you're done. And these are some of the elements that we have tested. I don't have the time to go over the details how you need to basically make sure that the material you fill this shell acts compositely with UHPC shell. You got to be careful, okay? And if you do that, this is a same size T-beam using a normal strength concrete. This one is a UHPC shell with the normal strength concrete, both same cross-section area. And you can see that that little bit of a UHPC, how much increases the strength. So this is another concept that using a UHPC. So your formwork is made of the UHPC, basically. We are looking at the retrofitting of timber piles using a UHPC. I think, and basically we are trying to use the existing piles, timber piles, as a formworks. And that 1.5 inch UHPC wrapped around that timber pile, really, that's all you need. So your strength is going to be dependent on that. So this is still research in progress. Another area that we're working is a barrier system. And the barrier system to precast deck with the connection using a UHPC. That's another area that has lots of promises. One more area, automations, robotics, automation. In future, the construction actually is where the robotics have been slow to find its way, but over the next decade or so, you're going to see more automations. So we are looking at we are building our own, basically, robots in order to deposit the UHPC to build basically the different bridge elements. In particular, for example, we are printing UHPC shell that I showed you using a robotic. So now imagine that you can print these shells out of using a robots that can work 24 hours and then ship it to the site, stack them on top of each other's, and then fill them with the, let's say, lightweight concrete. So it's a tremendous opportunity there. Another area that we are really are excited about is using a shotcrete, using a UHPC. It may come as a surprise to you, but we are also looking at using a shotcrete for bridge deck overlay. We believe that this approach using a UHPC and a shotcrete is going to provide us with the opportunity to retrofit our deficient bridge elements very effectively, very economically, because you don't need a formwork. But it's a process that still under the development. I can tell you in Europe, they had used it. You can shotcrete this thing overhead. You can shotcrete these element that are in a vertical position or horizontal positions. We have developed some equipment for this. I can tell you that we are almost there, and we are hoping that within the next 6 months, we should be able to roll this product out. And I think this is one of those technology that's going to make a paradigm shift in the bridge retrofit bridge technology. So stay tuned for this. This is a very exciting area that is coming up. Those were the UHPC. I wanted to show you just 2 more slides, and then I'm going to be done. And Rick, I'm also timing myself, so I'm going to finish at 15 minutes, so just to make sure that I'm not running into the others' timing. The folded plate bridge system is a system that we have developed that is used now in several states. It's best suited for ABC application for shorter span. And finally, another technology that we're using, actually we're doing work right now to automate, is we have developed a magnetic method-based approach to inspect the condition of any steel element that is embedded in a concrete. This could be a steel strand in a pre-stressed concrete. It could be a steel strand in the duct in the segmental concrete bridge. And it is working fantastically. This is a technology that with a friend of mine at Technical University of Berlin, we have developed, we have applied to 2 bridges in the Florida. So this product is ready. So if you are interested, please get in contact with me, and I will be happy to share more information. So with that, Rick, that's my end of my presentation.
Thank you very much, Dr. Azizinamini. So I have noticed during our first couple of presentations, a few folks raising their hand. I'd highly encourage you to go ahead and just implement a question inside the Q&A. and we'll get it to all of our speakers at the end of the session. So if you would please do that, we would appreciate it. So I'd like to now pivot to our reducing cracking and bridge decks. Dr. Tyler Lay has more than 20 years of experience in the fields of structural and concrete materials engineering. During this time, he has worked as an engineer with a design consultant, construction contractor, government agency, and as a professor. Some of the awards that he has received include the Halliburton Excellence Young Teaching Award in 2011, the Williams Foundation Professor in 2013 for College of Engineering, the ACI Walter P. Moore Faculty Achievement Award in 2014, the Researcher of the Year Award from the College of Engineering in 2014, Halliburton Excellent Young Professor in 2014, the OSU Regents Research Award in 2014, and the ACPA Martin J. Knudsen Award in 2017. And he was also named the Outstanding Professor at Research University by the Oklahoma Foundation of Excellence in 2018. He was named one of the most influential people in concrete industry by the Concrete Construction magazine in 2019. Lay is very active in the American Concrete Institute, where he is a voting member of the Concrete Durability, Material Science, Concrete Portioning, and Sustainability Technical Meeting. Dr. Lay.
Thank you so much, Rick. What a great introduction, and it's so exciting to be back at ODOT Research Day. I really wish we could be together in person, hopefully we will really soon. But I'm really excited about this opportunity to share some of this work that we've been doing on reducing cracking and bridge decks with something I call a baby aspirin technique. You're like, what? Don't worry, I'm coming up to that, explain all that just coming up. And a big thanks to Aaron and Michael. They are the students that did all the work on this. They are amazing people, and I'm super excited what they're going to be able to do in the concrete industry together, because they're actually married. That's pretty cool. Concrete brought them together. I want to acknowledge the Oklahoma Department of Transportation and all the folks listed here, Walt, Matt, Teresa, and Brian for all their help, and Caltrans as well. So my friends is there. They've been big, major influences and also great people to bounce ideas off of, and I'll explain that coming up. So why is this important? Well, bridge repairs are costly. They're dangerous for our workers, our traveling public, and cracks inside of our concrete provide direct paths for outside chemicals to penetrate inside our bridge decks. We don't like cracks. We want to fight cracks. But we need methods in our toolkit that are effective, simple, painless, low cost, and have minimal side effects. And that minimal side effects is a big deal. That's a really big deal, because anytime we add complexity to the already complex world of construction, things just get crazy. And this is what we want. We want something like a baby aspirin. You know what I'm talking about, right? A baby aspirin is like a small piece of medicine you take. It helps your heart every day. It's not that much. There's no side effects or minimal side effects. That's what we want to stop our cracks. I'm going to be talking about two baby aspirin techniques today. One of them is called using a shrinkage-reducing admixture, and the other one is macrosynthetic fibers. Now, let's start with SRAs first. Now, there are definite drawbacks to shrinkage-reducing admixtures, and I know there's many people that have studied them in the past, and it makes it challenging to entrain air inside of our concrete. That is a challenge. They are costly, and they also impact our strength, and this has all been a reason why people have not used them. We're going to see if we can if we can address these issues one by one, though. We're going to start out testing some typical concrete that would be used for a bridge deck in Oklahoma: a 0.45 water to cement ratio, 20% fly ash, about 6.5 sack mix, and we're going to be using various dosages of shrinkage-reducing admixture. We're going to actually cast strain gauges inside of our concrete, and we're going to cure them for 7 days to simulate curing that would happen on a bridge deck. And then we're going to store it at 50% relative humidity and 73 degrees Fahrenheit. And then we're going to see how that strain changes over time. Now, I'm showing on this graph, on the y-axis is strain, okay, how much it moves. And on the x-axis is time, right? And as you're curing your concrete, concrete is like a hard sponge. That's what's going on. So as you cure and add water to it, look at that. It grows, it expands. And then once you put it in a drying room, this is a 73 Fahrenheit, 50% relative humidity, the sponge shrinks. And the one with no SRA shrinks the most. Then here's 1%, 2%, and 4%. You say, whoa. How does this work? Well, the shrink-reducing admixture changes the surface tension of the water. That changes the stresses on the concrete. If you didn't understand anything I just said, it's okay. As you add more SRA, you get less and less shrinkage. So as engineers, we usually say, I want the best. Give me the best. Give me the highest dosage I possibly can. And that's actually what most admixture companies recommend you use, is right around this dosage. But we're going to show that if you use around 1% SRA, you still get a lot of benefits. You get about 28% reduction in the shrinkage here at about 30 days. And this early age shrinkage is really important. So higher dosages of SRA, that does equal more shrinkage. But this 1% shows a lot of promise. Reduces our shrinkage by about 28% at about 28 days, and a little bit less at later days. But this early age shrinkage reduction is a big deal because it gives our concrete time to gain strength, and it doesn't have as much strain that it has to resist. Let's look at strength, the actual compressive strength of this concrete. Again, here's strength over here. Here are days, and these green line here is no shrink-reducing admixture. Here is 1%. Here is 2% and 4%, and that's 1% by weight of cement. And as you can see here, this 1% has almost the same performance. 1% SRA doesn't lose strength, but look at this. At 2%, we lose, and at 4%, we lose even more. Side effects. We don't want side effects. 1%, though, shows some promise. So an SRA dosage increases, then decreases in strength. So as SRA dosages increase, the strength goes down, but there's no statistical difference in the strength at a 1% SRA dosage. And so what does this mean? This 1% shows a lot of promise. It reduces our shrinkage by about 28% early on. It has no impact on our strength. And because we're using such a low dosage, it's less than a 5% increase in the cost of a typical concrete mixture. And baby, that is what a baby aspirin is all about. That's what we're shooting for. This is 1% is definitely a baby aspirin. Now let's talk about fibers, change. And we had some folks talking earlier about steel fibers. We're going to talk about something different. These are called macrosynthetic fibers. They're plastic fibers that are actually pretty high stiffness, not as stiff as steel, but pretty high stiffness. And we're going to say, how do they work inside concrete? And we've actually developed a test to evaluate this. We call it the split beam test. You take a beam and you cast some steel wedges in them. You take a platen and you load them from the top and the bottom. And these wedges are important. They're not connected at the bottom, so they can move back and forth from one another. So as you push down from the top and the bottom, crack. That's what we're trying to avoid. That's what we're trying to fight. There's no connection there. They move apart. You can the mechanics actually works out beautifully in this test, and you can actually come up for what kind of axial load I put on this, what kind of tensile strength I'm getting. It's kind of like a indirect tension test. And this beam is only supported by the top and the bottom, so it's like floating. It's floating in midair. You might say, whoa, whoa, whoa. Doesn't the self-weight cause tension? Yeah, but it's minimal to whatever loading that we're going to put on it from the top and the bottom. So we're going to actually cast a number 4 bar in the center of this. And we're going to cast fibers in it as well. Why do we do that? Well, once it cracks, the bar takes that initial load, that shock, and then we can see how the fibers do how they perform in keeping those cracks small. So here's the video. We'll watch it twice. So as it starts to go in here, it's loading, loading. You see the crack kind of creep, 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 creep. And we're actually measuring it. We're using a crack card to measure it 3 different places on the top and on this face, and 3 different places on the back face as well. And so we can see for a given amount of load how much cracking. We'll watch that again. Here it is. Crack, creep, 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 crack, crack, crack. We're measuring it, measuring the sizes of the cracks, doing it. Now we're using something very simple, a crack card, just a little card you can hold up and actually measure the cracks with. You can change because they got a chance to work. So on the y-axis here, this is the size of the crack. And on the x-axis here, this is the load that we actually applied. The red line here is just the rebar, no fibers. And the other lines here, the 3 pounds, here's 6 pounds, and here's 12 pounds, different dosages of fiber. And as you can see, as the fiber dosage went up and up and up, the crack sizes for a given amount of load got smaller and smaller and smaller. There's actually 3 zones of behavior in fiber reinforced concrete. In zone number 1, the fiber dosages actually all perform fairly similar to one another. They keep the cracks smaller, and we'll talk more about that coming up. In zone number 2, the performance with increasing fiber dosages, right? And then in zone number 3, the fibers start to debond and pull out. Now, this may be a little bit different, and this is a little bit different for steel fibers. So again, we're talking about macrosynthetic fibers today. It's pretty cool. But we care about zone 1 and zone 2 for the most part, for durability, keeping those cracks small. So let's zoom way in here, and I'm just going to pick a crack. Well, actually, I'm going to show it. Here's the rebar at the top, and here's the rebar plus the fibers at the bottom. And again, look at these. The fibers are all doing a good job. They're all keeping the cracks small, and then all of a sudden we start to see a little bit difference in performance here. But at a crack size of about 0.03 inches, and that's one in the literature people talk about. That's an ACI recommended crack limit for certain sizes structures. Then we can see this is where our rebar is, and here's where our 3 pounds of fibers, that's about a 30% decrease in the crack size. Here is 6 pounds, that's about a 60% decrease in crack size. And here is 12 pounds, that's about an 80% decrease in crack size. You might say, whoa, that's cool, but I just can't really conceptualize this. Here is our friend, the crack card. And what I'm saying is with no fibers, the crack would be here. At 3 pounds, it would be here. 6 pounds, it would be here. 12 pounds, it would be here. That's cool, right? We can visually see how it's impacting our crack size inside of our concrete. So crack size is less than about 0.01. All fiber dosages were about the same. Greater than 0.01, fibers start to do their thing, start to help us. And for larger crack sizes, fibers start to fail. But I know what you're asking out there, because I was. How do these fibers impact the finishing of our concrete? Oh, well, we got another test for you called the float test. Now, this test actually is a 3-foot by 2-foot form that's 3 inches deep. You fill it full of unconsolidated concrete, you strike it off, and then you start to finish it back and forth. Oh, I left one point out. You actually form 3 1-inch diameter holes that are 1 inch deep. Why do you do that? Because when you strike the concrete, you want to simulate aggregates being plucked out of the surface. And we're going to measure how many passes it takes to finish the surface, to smooth the surface out and to close the holes up. Let's show you what I'm talking about. So there is the concrete struck off, right? Then we come in with this template. We form 3 1-inch diameter holes. And then we come in with this float. This float has been trimmed, so it only rides on the concrete, not on the wood. It actually has a yoke over here. It holds it at a fixed angle. It goes back and forth. We actually moved at a fixed speed, and we say, how many passes does it take to do 2 things? To close the holes and to make it smooth. What am I talking about? Closing the holes. So here's some holes at the beginning. This took about 4 passes. Between 4 to 6 passes is a really, really good performing system or mixture. Here is the surface texture. There is poor surface texture. There is the best surface texture. We don't need the best for our concrete. We can live with 10 to 30% overall surface voids, and that's what we're shooting for. That's what we want. And we want to know how many passes does it take to get there. So again, we can start to see how these fibers work. Here's 4 pounds per cubic yard, which is a pretty low dosage of fibers. This is what it starts out at. Here's 4 passes. Here's 7 passes, just a little bit more finishing needed with this fibers. If we go up to 8 pounds, a lot of people say more is better as far as fibers go, but look at this. It took 10 passes to finally get that concrete to close up. And you can see it still has a few issues in it. That's not good. That's not a baby aspirin. We want to make it as easy as possible for our people on the field, because then we have a chance to get it adopted and get people to use it. Now here's 12 pounds per cubic yard. Look at that. At 12 passes, it still wasn't finished. It still wasn't good. That's unacceptable. So fibers have an impact on the finishing and the slump of the concrete. But if you use about 4 pounds per cubic yard, you can reduce your crack size by 33%, and you barely know it's there. You may need a little bit more water reducer to make it work out. And so 4 pounds per cubic yard, that's another baby aspirin, and that's what we want. So what's the plan? What if we combined this macrosynthetic 4 pounds per cubic yard, baby aspirin number 2, and this 1% SRA, baby aspirin number 1, and we're going to get a powerful result. Pretty amazing. We're going to be able to go from conventional concrete cracking here to these things combined together to a 60% reduction in the crack size. for less than 5% increase in cost, or about 5% increase in cost, and you're not even going to know it's there. And we're building bridges. Division 5 has jumped in. We're working with 2 other divisions right now, talking them through their plan sets to actually do this on several spans and compare and see in the field and measure these cracks. And Bridge Division's working with us to write a special provision. We're super excited about all their help with this, and I'm glad that you guys are fired up about implementing this. Now, Caltrans has been doing some version of this for some time. It's much more complicated, much more sophisticated, and they love the approach that we're taking to streamline this process and make this easy. They love baby aspirins. So in summary, 1% by weight of cement dosage of the SRA can reduce your shrinkage by about 28% at 28 days and have no impact on strength. And it's 4 pounds per cubic yard of the macrosynthetic fibers reduces crack size by about 33%. And they together do amazing things. And this is a very, very simple way to improve your bridge deck cracking. So, hey, I just want to tell you, I've got a YouTube channel. Yes, a YouTube channel. You should check it out, youtube.com/Tyler Lay. Please like, subscribe, leave me a comment. I get about 10,000 views every day from people all over the world, all about concrete. You should check it out. Thank you so much for having me. Go Oklahoma, go ODOT, go SPTC. I appreciate it. Take care, everybody. Bye.
Thank you very much, Dr. Lay. As always, we appreciate your passion, what you bring to these presentations. Thank you very much. So shifting to mitigating calcium oxychloride deterioration in cementitious pavement, paste and concrete. Dr. Hale is the head of the Department of Civil Engineering at the University of Arkansas. He has served in that position since August of 2016. Hale has been with the University of Arkansas since 2002. In his research, he is focused on improving the performance of concrete and developing industry standards for new types of concrete. One of his most recent projects involved finding a solution to cracking caused by a process called alkali-silica reaction, which has been comprising parts of the Interstate 49 south of Fayetteville. Hale received his bachelor's, master's, and doctorate degrees from the University of Oklahoma. He has received the George D. Nasser Award from the Precast Pre-Stress Concrete Institute, the Charles and Nadine Baum Award for teaching from the University of Arkansas, and the Outstanding Teacher Award from the Department of Civil Engineering. He is a fellow of the American Concrete Institute and was selected to participate in the National Academy of Engineers Frontiers of Engineering Education Symposium in 2010. Dr. Hale.
All right, thanks, Rick. Okay, can you see my presentation? Hopefully you can. One, I don't know why I did to offend Rick. He put me after Tyler. So the opposite of Tyler's passion is me. So here we go. So first I'd like to recognize Casey Jones. He's one of my PhD students. He's finishing up this year. He did the majority, almost all of this work. The work, he was the brains behind the idea. He's developed the research, got most of the funding for it. So Casey's the expert. He and his wife just had their first kid. So you now have me to give the presentation and not Casey. But anyway, we're going to talk a little bit about Casey's work on mitigating calcium oxychloride deterioration. So a little bit of the background, make sure I don't go over. So we're going to go over kind of what calcium oxychloride is, some of Casey's research, and some of our limited conclusions. So calcium oxychloride is a chemical interaction between either de-icing salts, which can be calcium chloride or magnesium chlorides, and then the calcium hydroxide that's in the cementitious paste. So we all remember back to our cement chemistry, where the main strength component to harden concrete is the calcium silicate hydrate. Then you also have the calcium hydroxide. So what happens is the de-icing salts, whether they're calcium chlorides or magnesium chlorides, they interact with the calcium hydroxide to form this calcium oxychloride. So here's a couple of pictures that Casey took. These are the bottom of some 4x4 inch by, I think, 12-inch concrete beams that we use for modular rupture testing. So
Dr. Hale,
this
I hate
is,
to interrupt you, but could you please put your presentation in presentation mode? It'll be a
I
little.
thought, is it not?
No, sir.
All right, so here, let me, two screens going. Let me do this. Sorry. Is that better, Rick? Okay,
Yes,
sounds
thank you
good.
very much.
Yeah, sorry about that. See, that's what you get when you put me after Tyler. So anyway, so here's some pictures that Casey took of some of the calcium oxychloride that had formed on the surface of some modulus rupture specimens. So that they measure about 3/4 of an inch in length. So this calcium oxychloride, it can occur without freezing temperatures. It can be around 5 degrees C. The expansion product can be roughly a 300% increase in size where, you know, water freezes. It's about a 9% expansion. And you know, the 300% expansion is basically due to you're combining your de-icing salts, your calcium chloride, plus your calcium hydroxide and 12 water molecules to give you the calcium oxychloride. So it's a bigger compound. But anyway, it's significantly larger, and that expansion within hardened concrete can exceed the tensile strength of it and cause cracking. So kind of the formation location. So here's a concrete pavement, I think in Fort Smith area, and the middle western part of Arkansas. And so you have your concrete joints. You zoom in on the joints. Here's the concrete joint. Here's the tine, so you can kind of see the magnification. So it's a tine concrete pavement. They have some cracks here that run perpendicular to the joint. So even if the joint is good, there can still be some of the de-icing salts that get into the concrete. And then they can pond. If the joint fails, it can pond around the bottom of the joints. And then you have the de-icing salts along with the calcium hydroxide, and that can lead to some of the calcium oxychloride forming. So, all right, so here's the bottom of our concrete joint. Here's our de-icing salts, and you can see here that they can get some pore space interaction between the chloride ions, calcium ions. We have our calcium hydroxide. If we're in an air void, that's great because the calcium oxychloride can form within an air void. But if it's not in an air void, it can form within pores or within the concrete and cause some cracking, and that cracking can cause some propagation of the cracks and lead to additional deterioration. So one of the things that we looked at, or Casey looked at, some of the mitigation techniques. So we looked at supplementary cementing materials. We also looked at some inert fillers. Looked at entrained air, he did. And then there's also preferential carbonation and sealants that can be used. For Casey's work, for this, what we're presenting today, he looked at some rice husk ash. In Arkansas, I think we're number 2 in the production of rice in the world, I believe. And so we have a lot of rice husk ash. And so we were encouraged to include some of that in our research. And so you can see this really dark. This is after they burn off the rice husk ash. This is the ash part that's been sieved through, I think, a number 200 sieve. There's fly ash and bottom ash. And then we also looked at some inert fillers, such as limestone dust, some granite dust, and sandstone. So the first thing we'll look at is paste. And, you know, we're just talking about paste, which is cement and water. And we looked at the reduction in cementitious contents or additions of Class C fly ash of 10, 20, 30, and 40, 50%. We used a mortar paste mixture with a water paste ratio of 0.45. That's what the Arkansas Department of Transportation requires. That's the maximum water cement ratio that they require for their Portland cement concrete pavements. We made cubes, the 50 by 50 millimeter cubes. they were stored 91 days in a lime water bath, and then they were stored additional 91 days in a 30% calcium chloride solution at 5 degrees C. And so the 30% calcium chloride solution is what was typically, or what has been used in previous research. And so we kind of piggybacked on that. We looked at mass change, and then we looked at the LTDSC, the low temperature differential scanning calorimeter. Dr. Royce at Oregon State has one of those. We don't at Fayetteville, so we send a lot of our samples off to him, and then also to the CP Tech Center. So just kind of a visual representation of the deterioration. So once again, these are stored in lime water for 91 days, taken out, then put into a 30% calcium chloride solution for another 91 days. And I mean, you can see visually the damage that occurred and how well the fly ash did at mitigating that damage. So you can start up here with cement only, and then increasing by 10% down to where we get to 50% fly ash. So, the idea is the fly ash comes in, it reacts with the calcium hydroxide, it consumes it and forms additional CSH. So if you don't have as much calcium hydroxide, you won't have as much as the calcium oxychloride that forms. It just kind of shows the reduction in strength, and then also the amount of calcium oxychloride per compressive strength reduction. So on the left, we have our average compressive strength reduction. So, the first picture back here, you can see didn't have a whole lot of strength left at the end. You can see that we had about a 70% reduction in compressive strength. And it follows a general line. And so, these are, 3 to 6 mortar cubes tested per age for each one. And you can see that as we increase fly ash content, we see a decrease and the reduction in our compressive strength. So it's closer to what it originally was at 91 days of age. You can see even the 50% saw a little bit of reduction, a little bit being 20% after the 91 days in the salt solution. But likewise on the other graph, so this is what we get from the LTDSC, the average calcium oxychloride in grams per 100 grams of paste. You can see that on the y-axis you have the average compressive strength reduction. So same thing, it follows the kind of reverse trend. So there's 50% fly ash, 40, 30, 20, and then up to 10 and 0. So we have less calcium oxychloride at 50%, and then as we increase our or decrease our fly ash content, we have more calcium oxychloride. Likewise, mass change. So we looked at the change in mass, and this is after the 91 days in the calcium chloride solution. So this is a gain. So as you store the cubes in the water over time, and the calcium chloride or magnesium chloride, the salt solution, 30% CaCl, it cracks, but the cracks allow more of the calcium oxychloride to grow in there. And so there's actually, you're not losing parts of the cube, it's swelling, so you're gaining strength. And you can see that here at 91 days of age in the salt solution, we gained about 9% for the control mixture. You add 10% fly ash, the gain is only about 2.5%, 3%. And then the other ones, I mean, they basically remain the same, maybe a 1% decrease in mass. But you can see the noticeable decrease from the control mixtures down to, as we increase fly ash, this average mass change decreases. And then likewise, when we look at fly ash level, the percent, you can see that the average mass change was 9% for the control mixture without fly ash, and as you add fly ash, the mass change decreases. And then finally, if we look at the cement paste comparison, so mass change on our x-axis, average compressive strength reduction, you can see there's kind of a breakover point And so we have the average compressive strength reduction. So here's 50%, 40, 30, and 20, and then 10 and 0. And as you see that the slope of the line kind of changes between 50 to 30% and 20%. And then when you have 0 flash replacement rate, once again, you see the 70% reduction. Likewise, on this chart, the calcium oxychloride content, when you have lots of fly ash, it consumes that calcium hydroxide, so there's not as much calcium oxychloride. And then as you move up here, where you have 10%, you have more calcium oxychloride. Then we moved on to the concrete testing. And so this is actual concrete. We looked at 15, 30, and 45% replacements with Class C fly ash. Our air entrainment, Casey was really good with the air entrainment. He hovered between about 5.8 and 6.3%, 5.8 and 6.3%, 0.45. We followed our standard RDOT requirements. We made cylinders, the 4x8 inch cylinders, and then like the 4x4, about 400 millimeter MOR specimens. We cured in a 91-day cure in a lime bath. The 202 is kind of a, let's say, kind of a screwy number because the COVID affected us. The University of Arkansas was shut down for a little bit this spring, and they didn't allow anybody into the labs. And so that number changed a little bit. It wasn't originally going to be 202 days, but we couldn't come to campus, and that's why it's at 202. So here's visual. So these are cylinders, okay? These are cement-only mixtures that were stored in a 30% calcium chloride solution. Here's the MOR specimens, and you can see that, you know, there's not much strength left in any of these. These can't be tested. And then if we look at fly ash contents from 0 fly ash to 15 to 30 to 45, you can visually see the increase in durability, I would say, resistance to calcium oxychloride that you can see with the increase in fly ash. So just quickly here, we'll go over this. This is compressive strength difference. And we labeled this as 0 just because those Portland cement only mixtures really couldn't be tested after the 202 days. But the fly ash level at 15%, we saw a decrease in 20%, and then they were close to about the same at 30 and 45% fly ash. The flexural strength, that was our modulus rupture, our measure of tensile strength. Once again, the cement-only mixtures couldn't be tested. The other ones, we didn't really see as much difference, but you know, it's tensile strength. For those of you who've done tensile, there's, you know, I think our tensile strength is about 800 PSI. So there is some variability in just the test results. And then mass change, we had a pre-wash and a post-wash. Well, the pre-wash, Casey just kind of gently got some of the stuff off the outsides of it and measured it. The post-wash, as you can see the gray one up here, that's when he got, it wasn't a pressure washer, but gently ran kind of a water hose over the concrete to get all the stuff up and remove the loose concrete. And you can see that the cement-only ones lost about 65% of their mass. When you added the 15, 30, 45% fly ash, you can see they didn't lose much mass at all, which is also evident in the pictures. So we did a little bit of chloride ion penetration. You can see that, and I'm running out of time, but this, I will say, started off as a prism, and then over time, this was the core that was left, and you can see that the dark circle or dark gray is the ion penetration over time, and as you increase fly ash, that distance is less and less. So I'll move on past this and just end with our conclusions. So our calcium oxychloride can be a serious concrete deterioration mechanism, occurs in the jointing regions. We found that fly ash is an effective way to mitigate it. We found some deterioration even with 50% fly ash. In the paste specimens and concrete, we saw a little deterioration at 30% or more, and we did see some chloride ion penetration with 45%. Then last but not least, we want to thank Weaver Bailey, Garver, Oregon State did a lot of testing for us. ACPA sponsored the research along with RDOT, the CPT Tech Center, and then the University of Miami. So that's it.
Thank you very much, Dr. Hale. We have a couple of questions that we'll get to real quickly before we move on to our next session. So the first question I'll pose to the presenters is, what is cost comparisons of proprietary and non-proprietary UHPC?
So I guess I can start on that one. And it's kind of a hard comparison to make because there's a lot that goes into proprietary UHPC in terms of the support that you get from the manufacturers, and some of their projects come as kind of a full package. But if you kind of look at the material, the proprietary UHPCs are in the maybe $3,000 per cubic yard range, where the non-proprietary UHPC that we've seen both from our work and some of the others we've collected from around the country, about $400 to $700 per cubic yard. So again, very small jobs where you maybe just want to do a few repairs, you can get a significant cost reduction using some of the non-proprietary UHPC that may not be as significant on a very large project.
Thank you, Dr. Floyd. Dr. Azizinamini?
Yeah, I think just to add, the price of the UHPC per cubic yard, you will hear some really high numbers, but if you take a close look at it, really it's not the cost of the material, but it's cost of for example, for the proprietary, the technicians have to be on site, they have to have their equipments and so on. So those really are adding to the cost. Just for your information, we are also interested in using a UHPC in certain applications where we don't need the fibers. And if you can eliminate the fibers and just rely on the strength, then the cost even goes much, much lower than what Royce was saying. And so the non-proprietary, I think, is by the time of the production probably will be in order of probably 5 times less than the proprietary, I would say.
Thank you, sir. So Dr. Floyd, considering pullout is not really a compressive mechanism, what is the justification behind normalizing the pullout result with respect to compressive strength? Would it not make more sense to not normalize with respect to flexural strength?
That's a good question. And we thought about that when we did this, and we were trying to kind of eliminate or isolate, say, the bond testing properties. And we're, still kind of in progress on getting the best answer there. But the main reason was that we didn't have tension data that was companion to those specimens, but we did have compressive data. We looked at it in terms of the compressive strength as well as the square root of compressive strength to approximate the tensile strength. And we got a very similar comparison using the square root of tensile strength. But I'm going to go back and see what data we have, talk to the students to see, if there's a way that we could try to make a direct comparison with some of the tension strength data that we have. It was just that we didn't have companion specimens for those particular mixes.
Thank you, Dr. Floyd. So talk to us a little bit about how it's sensitive to temperature exchange during placement.
So it's a good question. So say for very cold temperatures, it's going to take a lot more time to set and to reach strength, which is going to be similar to a lot of your conventional concretes. In very hot temperatures, you're going to potentially lose workability very quickly. And you also have to be very careful to protect it from evaporation. This is a material with a very low water cement ratio, so there's not a lot of water in there. So you need to protect the surface from drying out and causing a lot of plastic shrinkage cracking if it's really warm. And then, the same is true for the surfaces that you're casting UHPC against, but that's not really temperature dependent. But really the main things is the time it's going to take to set if it's really cold, and the loss of workability if it's really hot.
Okay, great. So talk to us a little bit about what the difference in performance between casting the UHPC around a beam versus using it as a shell.
Let me add, I think the difference in the performance, like Royce also showed, this material is nothing really penetrates through it, and all you need is just an inch or so of the material to really protect to what's inside. What inside that UHPC shell could be normal strength concrete, could be lightweight concrete, and you should be protected. Now, it is important to get a good composite action between the two materials. And to get a good composite action, the problem is different than casting a normal strength concrete, let's say, or UHPC around the normal strength concrete. In this case, you will need some type of a mechanical action in order to have a good composite action between the UHPC that's already hardened and then the normal strength concrete that you're going to put inside that. And if you do that, then you should have the very good performances.
All righty, thank you very much to all our presenters. That does conclude session 1. Very appreciative of all the information provided, and the ability to not have any technical difficulties was great. So I appreciate the staff in that regard. So I will at this time turn it over to Mr. Uden for our next session. Thank you.